Hello everyone. Today we're talking about gradient vector. And the question that we're trying to answer today is what is it about combining partial derivative with respect to each variable, keeping the other variables constant, into a vector gives us the direction of steepest ascent. One thing that I want to be clear about is that the gradient vector is actually on the xy plane. We are restricting ourselves to two dimension, and when we talk about two variables, this is the what the vector looks like. This is where the variable is. It's in the plane, and in the z direction you have your function f of x comma y. You can just as easily extend this to higher dimensions. If you add another variable, say z, then in that case you have a gradient vector that is in the space, in the 3D space. But we're today restricting ourselves to two dimension, only two variables, because that is way more easier for us to understand. But this can just as easily be applied to higher dimensions. So this is an example. Down here at the bottom, you see it's the xy plane, and this is the surface. It's coming out of the plane in the z direction. And the vectors on the xy plane that you see here are the gradient vector at any point on the xy plane. And you see all of them are actually pointing towards their local peaks, their local maxima. So now I'm going to break down the components of the gradient vector for you, which are partial derivative with respect to y and x respectively. Now let us look at a point a comma b. These points are the intersection of two lines that run parallel to the coordinate axes, and those lines are y is equal to a and x is equal to b. When we take these two lines and slice the surface through those lines, these are the two curves that we get. And when we find the tangent line here and here, that is basically the derivative that we get from it. Going back to calculus 1, we know that derivative is basically the tangent line to the curve, which has a value of tan theta, where theta is the angle that the tangent line makes with the coordinate axis x. Now, when we take this to a higher dimension, we get angle that's made with two axes, both coordinate axes, and we replace the derivative value with tan value, so it's easy for us to understand, even more so because tan value is the least when the angle is 0 and maximum when the angle is 90 degrees. So it has like a proportionality relation with the angle. Now, the next thing that I want you to recall is that when the angle has a component that's larger in x direction, then we have the angle that's tilted more towards x. And when we have an angle, we have a vector that has larger component in the y direction, the angle of the vector is tilted more towards y-axis. Applying that to our previously found equation, we know that the gradient would be more towards x-axis when the partial derivative of x is larger, of the function is larger in x direction, that is in y direction, and vice versa. Now I want to talk about one particular example where tangent in one direction is practically 0. We're talking about a point P, x comma y, where This is totally zero. This is parallel to y-axis, so it has an angle 0 with y-axis. Now we have a vector that has one component that's completely zero. What that means is that the value of this gradient vector is going to be, this vector is going to run parallel to x-axis. So this is what we find here. This vector runs parallel to x-axis and it goes straight towards the maxima. It points towards the maxima. I've used this example because it clearly shows why the gradient vector points in the direction that it does, but the general idea is that whatever has a larger value, the gradient vector would lean more towards that direction in xy plane. So if some other case where partial derivative with respect to y has a larger value, then it will lean more towards like the y-axis in the xy plane. Taking another example, for instance, here we have two angles. Let's say they both are equal. They both have equal value of the derivatives. In that case, this vector, this gradient vector, would have equal value. That means the vector from a comma b is going to have an angle of 45 degree with respect to x is equal to b and y is equal to a, which again seems to be going to the local maxima, which is at the z-axis, points towards the z-axis. Here, it won't completely make sense if we totally start moving towards parallel to y-axis or parallel to x-axis. There's this sweet spot in between these two lines, which perfectly aligns with the gradient vector going in the 45-degree angle to this point AB. To help you generalize this idea more, I want you to imagine being on an xy plane. Suppose you are at a point a comma b on xy plane, and you want to find what is my local maxima. Where is it? In what direction do I go to reach there? What are the two information that you have in your vicinity is what is the partial derivative with respect to x and what is it with y. Let's say my partial derivative with respect to x is higher, so my slope in the x direction is higher than it is in y direction. So I would lean myself to go more towards the direction that's leaning more towards x, but I would not completely commit myself towards x because I know that there's a certain slope even in my y direction. So I hope the examples and this analogy help you understand this idea better. In worst case, I just hope it gives you a certain insight into what it actually is. Thanks for watching.